One more time?
30.72 meters per second squared.
That is a large acceleration due to gravity. More than Jupiter.
The average person weighs how many kilograms?
Pardon?
The average person weighs how many kilograms?
The average person, I think, is about 70 kilograms. Has a mass of about 70 kilograms.
So on there, they're only 2,150 pounds, no, kilograms?
Be newtons.
Newtons.
Yeah, my weight is, well, it's roughly 3 times what it is here.
Okay.
Yeah, because we're 9.8, this is 30 point, this is roughly 30, so it's roughly 3 times. We would weigh 3 times more there. I do want to point out on the Jupiter problem on the test, I said you basically, when you're standing on Jupiter and you throw the rock straight up, something like that, you actually can't stand on Jupiter, even if you were in a specialized suit, because it's not solid.
I thought about that. I thought that was a trick question.
No, I just put it another planet.
Is the center of Jupiter solid? I thought there was something like.
I was thinking it went from gas to liquid. I didn't think it actually got to solid at any point, but I could be wrong on that. My astronomy is just stuff I pick up in the streets.
Could we see old tests?
I've got some posted, but
Because there's some that are like missing part of the answers.
yeah, at the end, remind me and I'll pull it out, and if you want to take pictures of it, you may. Any other questions?
So we have lab this upcoming Tuesday, and then would that not be due till like 2 weeks because of spring break?
Yes.
Okay.
And I'm gonna try to make the lab that we do on Tuesday short enough so that if you have questions, because there's a test in 2 days, after that, if there are questions, you'll have time to ask those.
There's stuff that we have to work on over spring break.
Pardon?
Are there stuff that we're gonna have to work on over spring break?
Well, test corrections I'd like before spring break, but if you're not gonna have them by then you potentially have that to work on. The lab would be due the Tuesday after spring break,
Okay.
so potentially you get that done before spring break, you don't have to worry about it.
I just wanna make sure because, we'll be working for spring break, so.
There's not gonna be any anything new. The Tuesday after spring break, you've got the lab and yeah, there won't be any quizzes announced yet.
So next
We'll not finish
Tuesday,
any of the new chapters yet.
so next Tuesday, we got a lab due, we got lab that day, and then Thursday we have our test.
Yep, and then the following week is spring break, unless I'm off a week. I don't think that's right. All right, projectile motion is not on the test, in case you were wondering that. So that's why I said, are you doing it just for fun? That was 1A. All right, so we'll sort of pick up on, this is sort of the first material on what traditionally has been the last test. First material that is not on test 1B. I'm going to set up a scenario here. And so I have object A traveling to the right, and I have object B traveling to the left. They are going to collide. Let's just say that they collide at this point right here. So this is when A and B meet. Now, the way I'm drawing it, it looks like the sides of A and B are changing. Let us not assume that they change in size, just assume that any changes in size are based upon my lack of being able to draw the same thing twice. They will make contact. They will make contact and then they will move. And then they separate. In this particular scenario, I'm going to have them bouncing off each other, but that's not necessarily the case. The generalized case is there's not enough information given to know what's going to happen after the collision. But for right now, just assume they bounce apart. Any questions on what this beautiful diagram is trying to communicate?
So we're assuming that B was traveling faster than A?
Yes, you may assume that. Here's sort of the visual. All right. Yeah, you can't get sound effects from the drawing. Although potentially, since it's videoed, I could add them in later. Why? I don't know. All right, so the question is, there are three quantities that are the same for A and B while they're touching each other. Three quantities that are the same for A and B while they're touching each other. What are they? And just to add a level of excitement to it, a little bit of danger, can you get them before you hang the man?
Acceleration.
Which? Pardon?
Are we doing both problems or just the hangman?
Well, as you guess, if you have an incorrect guess, then we'll start putting the man up. What are the three quantities that are the same for A and B while they're touching each other?
Acceleration.
Is not going to be the same for each. So we're going to acceleration
guys.
over here. A or, come from both there. It looks like basically my cousin Robert's head. Never seen anyone with as round a head as he's got. Yes,
Would their normal forces be the same? Since it's equal.
they're touching. Anyone want to qualify that?
We're talking about when they're touching.
Yes, while they're touching.
Okay, well, that would be right.
So close. Not the way you said it. I believe it's if you were writing it down, you would write it down correctly, but the way you said it, there's a small flaw to it.
Are we talking about
What did you say
directional? Their
originally?
direction, like the ones, we haven't made a coordinate chart, so I can't really say which normal forces that they're referring to.
So what is the same for both of them?
Normal force they exert on each other.
Right.
That's what I basically heard him say the first time. You mentioned a magic word that differentiates between your answer and the correct one. All right, so let's do it this way. Let's say I apply a 10 Newton force to the table, just then.
It applies one back.
It did. Now I come over here and I apply a 10 Newton force to the table that way. Did I apply the same force?
No,
Why not?
different direction.
All right, so back to this.
Okay. Sorry.
Say what again? Yeah, I guess I'll go with that. Same magnitude.
Oh.
Same magnitude of force.
Okay.
The directions are opposite. So what I'm going to write down here is sort of the shorthanded version of it. The force on A from B is equal to the negative force on B from A. The negative sign just indicating opposite directions, but the magnitudes are the same. All right, let's just, at this point, let's just assume we've covered the forces. If you bring up any other forces, I'm going to start adding to the body parts. All right, what other quantities are the same for both of these things while they're touching?
What velocity?
It would not. They start out at different velocities, so when they touch, that means immediately they're having different velocities. So velocity is not the same. They're also traveling in opposite directions initially. A continues forward for a little bit while B turns around at some point, so that velocities can't be the same.
Well, you said when they're touching, right?
Yes, while they're touching.
I asked their insurance company. So let me go ask the insurance company.
Well, I'll wait to give my really obscure clue. One of these is so incredibly obvious that usually groups think of it last. Almost have to drag it out of them. Because it's so incredibly obvious, people don't think about it. Pardon? Sophie?
Time?
Yes, that's the one that's so incredibly obvious. They touch each other for the same amount of time. My obscure clue for that one is it's also the name of a Bobby Sherman song, which usually prompts the thought, if not outright question, of who's Bobby Sherman.
Are we doing the same?
Bobby Sherman was a teen pop idol of the 70s,
Okay.
before there was any electronic manipulation of the voice, and his voice doesn't quite hold up over the years. I did have a student a number of years ago who had actually seen him in concert. His sister was a huge fan. Dragged him along. There's one more.
Or we assume that they're not starting from there.
Yes, you can assume that because they are heading towards each other. Sure. You want to make that? When you're talking about an object like this, when you're dealing with position, position is really the center of mass of the object. And so position doesn't quite work. I'm going to go ahead and add a body part, but just because you should have known. Should I? We'll add half an arm. It's my cousin Andy.
Wait,
Oh, sorry. Andy was born with a birth defect. His arm basically came here. Did I tell the Andy story? No. He was at one point he was in a department store sucking on the end of his arm. He was a small child, and some older woman came up and wanted to say something cute to him and said, "If you're not careful, you might swallow your hand." At which point he pulls out the nub and there's no hand there. His parents didn't explain. So you said position.
technically you gotta add the toenails. the hair.
I don't think there are enough quantities to get that far. And Ben was close.
Displacement?
Yes. Because A travels that far, B travels that far while they're touching. They touch in the same spot, they let go at the same place, so their centers basically move the same distance. So we end up with displacement. It's the same. All right, so why do I go through this? More than just be able to draw Barbie Sherman references, I'm sure. If I combine these two things right here, if I look at the forces and I look at the displacement, this leads us into chapter 7, which is work and energy and fitting markers. Work and energy. If we look at these two aspects of the collision, this leads us into momentum and impulse. Work energy, as I mentioned, is chapter 7. Momentum and impulse is chapter 8. We are taking the stuff that we have already done and looking at it slightly differently. There are advantages of doing this over F equals MA. There are times F equals MA makes a lot of sense, and there are times where work energy makes sense, times when momentum makes sense. Typically, if there's a collision, momentum is the way to look at it. If the forces are constant, I was about to say Newton's laws, straight up F equals MA makes sense, but that's not always the case. All right, so any questions to this point before we launch into the beautiful world of work and energy? And just to get at a level of excitement, we're about to do a derivation. A derivation. Letters all over the board. Yeah. I know sometimes the excitement is so much your brains just tire out really quickly. All right, so here we go. What I want to do is I want to look at the force being applied to, let's say, object A. So the force on A from B. And then I want to do a dot product with its displacement. I believe we talked about dot products early on, so a month and a half ago, 2 months ago, whenever class started. Who remembers what dot products are? Got 1.5, I think that was. All right, so not a lot of memory there. We've talked about adding vectors, we've talked about subtracting vectors. We are now dealing with multiplying vectors, and there's 2 different ways to multiply them. Dot product is one, the other? Yep. They're both looking at 2 different things. All right, so let's talk a little bit about dot products. Dot products are called such because you use a dot to represent it. A cross product is represented by a cross. Not a Christian cross, but an X. All right, so if I have a vector A dot B, I have vector A, I have vector B. What I'm asking is, how, if I take the amount of vector B that's in the direction of A and multiply them, what do I get? So if I have some angle between them, theta, what I need to do is I need to break B up into its components. Just like we've done many, many times. And so this part right here in green in the same direction as A is B times the cosine of theta. And then I multiply them. So A dot B would be A times B cosine theta. Or the magnitude of one times the magnitude of the other times the cosine of the angle between them. So, if 2 vectors are perpendicular to each other, so if I had A up like this and B like that, what is the angle between them?
90.
What's the angle between them?
90 degrees.
Thank you. What is the cosine of 90 degrees?
0.
A question like that, it was one or the other, it's 0. So if I have A dot B and they're perpendicular, what is the dot product?
0.
0. Yeah, doesn't matter what A and B are, because the cosine of 90 degrees is 0, you get 0. Notice, this 0 here does not have a vector symbol. Over here, the vector symbol has disappeared. Dot products produce scalars. This is also known as a scalar product. And this is the advantage of doing this, of going through what I'm about to do, is because we can look at a problem from a scalar point of view. We don't have to worry about the vector point of view. It's also a disadvantage because we lose some information when we drop the directions. Momentum, on the other hand, momentum deals with vectors, And so we have the advantage of keeping direction into it, but we lose information, but it's more complicated. All right, so quick plug and chug problem. If I have a vector 4 newtons, comma, 30 degrees, dot product with 7 meters, comma, 110 degrees. So if I drew that out, we have 4 newtons at a 30-degree angle, and then 7 newtons, or 7 meters, and that is 110 degrees. Not quite perpendicular. What is the dot product? Or what would you multiply together to get it? Was not expecting this much silence here. What would you multiply together to get it?
7 and 4. 7 and 4. No.
All right, so you multiply 7 and the 4, so I got 4 newtons times 7 meters times,
Cosine. Theta.
what is theta?
110.
So what did you say?
140.
No. What is theta? Conceptually, what is theta? Wait, all right, say it louder.
No.
Yes. 80, it's 80 degrees, times the cosine of 80 degrees. Theta is the angle between them. That's 30 degrees there, it's 110 degrees there. That is theta, that's the theta we care about, the angle between them. It's just the difference in the angles. So we get 28 Newton meters times cosine of 80 degrees, which is small, probably somewhere in the order of 0.1. So probably somewhere around 2 or 3 is the, with appropriate units.
4.86.
4.86 Newton meters. I do put a dot between the Newton and the meter, not that it's critical if you do it in that order, if you do a capital N, lowercase m. If you do it the other way around and you want to write meter newtons, it is also correct, but it is crucial that you have the dot in between. That is a meter newton. That is a millinewton. So typically when you have a string of units together like that, you put a dot in between them just to differentiate. And uppercase N is important because lowercase n, that's a nanometer. And if I put a dot in between, that's nothing because lowercase n, to my knowledge, is not any unit. All right, so let's do another one, except this time, let's not give it in that form. Let's give it in a rectangular form. So 3 newtons plus, let's make minus 1, 3 newtons I hat plus 1 minus 1 Newton J hat. There we go. Dot product, 8 meters per second I hat plus 3 meters per second J hat.
It's minus 1 Newton.
Yes, that's a minus there. So now, when you are multiplying these out, I'm going to do it the long way to start with, but there's a simpler way of doing it. I'm just going to FOIL. So we multiply the first ones together. So I'll get 24 I hat dot I hat. Now my units are going to be newtons times meters per second. So there's an implied newtons times meters per second sort of tacked on at the end. Outer plus 9 I hat dot j hat minus, now enter, 8 j hat dot I hat. And then last, minus 3 j hat dot j hat. This is not a final answer, because again, dot products give us scalars, and I still got vectors here, so we need to somehow get rid of them. So the question is, what is I hat dot I hat?
I squared. Zero.
Which is, pardon?
Negative one?
Oh, different I.
Okay.
Yeah, no, this is not the same I as you get to math class.
Zero.
Well, let's go to the formula then. We have our formula for doing dot products. So I have I hat dot I hat. That should be the magnitude of one of them. So what's the magnitude of a unit vector?
One.
So that's 1 times the cosine of the angle between them. What is the angle between I hat and I hat?
Zero.
Yeah, the angle between any vector and itself is always 0 degrees. So 0 radians or degrees. What's the cosine of 0 degrees? I think somebody said it briefly.
1.
Yes, so we're doing 1 times 1 times 1, which is
1.
all right. So I hat dot I hat is 1. So this is just 24. Because it's 24 times 1. Now, I hat times j hat. What is I hat times j hat?
0.
Why?
Because you end up with the same volume, the angle between them is 90.
Yeah, there. So that's 0. J hat dot I hat,
0.
same reason. And j hat dot j hat?
Minus 3.
Oh, times that, okay. So we get negative 3. So the final answer is 21 Newton meters per second. The shortcut, since the cross ones disappear, the I dot j and j dot i's disappear, the shortcut is just you multiply the like components. You multiply the I hats, you multiply the j hats, add. All right, I think we're ready. Oh, let's just do one quick plug and chug. So if I have, we'll drop units here. So negative 4 I hat minus 3 j hat, dot product 6 I hat minus 2 j hat. What do you get?
Sorry, 18.
Close. Yeah, negative 18. Negative 4 times 6 is negative 24. Negative 3 times negative 2 is positive 6. Negative 18. It's now, in my experience, everyone is now an expert on this. Actually, later on, when you get into more advanced mathematics, this is actually a test for whether things are perpendicular to each other or not, is if you have what's known as an area vector for two surfaces, then you can do a dot product. If you get 0, they're perpendicular. If you don't get 0, they're not. As a matter of fact, you can find the angle between two planes using this. But that's beyond the scope of what we're doing here. All right. We will do doing dots later also. All right, so I have a dot product here. What is force equal to?
Acceleration.
All right, so this is the mass of A times the acceleration of A, dot delta X. Acceleration of A. Now, for the sake of the next set of formulas, I am going to assume constant acceleration. You can also do this with calculus without constant acceleration, you get to the same place, but we will make the assumption acceleration is constant, so we can use the cake formulas. What is the formula for acceleration? So this becomes mass of A times V final minus V initial over time. T or delta T, whichever one you want. And dot product with delta X. We do have a formula for delta X. It's the one that Daniel mentioned earlier when we did the projectile motion problem.
Velocity final.
This,
Velocity final.
Oh,
That's velocity. Over 2 times t.
all right. So that equals that, which equals that. Now, things that are not vectors, we can just factor in, out as we please. Notice that time disappears. I have time in the denominator here, time not in a denominator there. They cancel out. I got dividing by 2 there. I'm just going to pull that out front, so we end up with a 1/2 MA VF minus VI dot VF plus VI. And now we FOIL. So I do the first ones. And so I have 1/2 MA times VF dot VF plus, we do outer, VF dot VI minus VI dot VF plus last, minus VI dot VI. About to simplify it. Questions on how I got this far? All right, here we go. VF dot VF. Pardon? Who? Not if you're stopping there.
VF squared. Or 1.
It's not 1. The other one was 1 because the magnitude was 1. The magnitude is not 1 necessarily.
Is VF squared?
It is VF squared. Because I multiply the magnitude of 1, which is VF, times the magnitude of the other, which is VF, times the cosine